Hi everyone. Um, so this is the first video clip for week number 12. In this video, I like to go over the slide that we visited before the spring break as a reminder, and I just want to go over the topic again briefly so that you can catch up those the informations, and then we can move on to the next level. So here is the slide that we went to before. And okay, so the first topic was the compactness. What does that mean? The compact mean in the steel design. So here's a definition to determine whether our sections are compact or not. And we use this formula. This formula is showing the ratio between BF over 2. So this is BF over 2 to TF, which is the thickness of the flange. So let's say here we have a typical W-shaped section. Sorry about the poor drawing. And PF over 2, I mean the BF over 2, BF is the width of the flange. So BF over 2 is going to be just half of it, half of the flange width, right? And TF is the thickness of the flange. So this is going to be thickness, right? So when we take a ratio between these two, that means it's kind of a slenderness ratio for this, the cantilever portion of the flange. And if that ratio is less than 0.38 times square root of E over Fy, then we can say our sections are compact sections. And as you know, the Young's modulus is 29,000 KSI for all steel, structural steel, and Fy, the yield strength of the material. Typically, we use a 50 KSI steel. So when we plug those two numbers and simplify the relationship between BF and TF, this is what it is. If BF is less than 18.3 times TF, the thickness of the flange, and BF is the full width of the flange, then we can say our sections are compact. And let's check it out from our steel manual. So let me go out. And here is it's my kind of DIY document camera using my old cell phone. Anyway, so it looks something like this. This is my old cell phone with tripod, so I can show you this portion of the steel manual. So anyway, when I just open up the random page in chapter 1, the dimension table, and I'm going to just show you how it works. So let's say 44 by 335, which is really heavy section. And here we have a dimension for the flange width and flange thickness, BF and TF. So pick just one number, 15.9 inches, the full width of the flange, 1.77 is the thickness of the flange. So 18.3 times 1.77, if that number is less than or larger than 15.9, that will determine the compactness of the section. So if BF, in this case, 15.9 and versus 18.3 times 1.77, of course 1.77 times 18.3 is going to be larger than 15.9, right? Because 18.3 is already larger than 15.9, and multiplied by the thickness larger than 1, so it's definitely larger than 15.9. So we can easily say that this W44 by 335 section is compact section. By the way, there are only a couple of the sections from our steel manuals are violating this compactness definition. So what does that mean? So only 11 exceptions, right? If you stay in the AISC part 3, that's the table for the beam sections, then most of the members, except only 11 sections, are meeting this criteria. So what does that mean? It means that compression flange, so when we have beams under the positive moment compression flange is going to be the top flange because top portion is going to be in compression while the bottom half is going to be in tension. So the compression flange, which is the top flange under the positive moment, will not be buckled locally before this beam reaches to its full capacity, okay? Which is good, right? So because we can utilize the entire capacity of the beam before we have any kind of a local buckling failure. Okay, so we're going to focus on the analysis and design of compact beams, and there are two cases that we're going to consider. One is laterally supported Y-flange beams. The other one is laterally unsupported Y-flange beams. So we have a Y-flange beams, the W shape used as a beams, and one is that we have a lateral kind of a bracing so that we have a additional lateral support to prevent lateral torsional buckling failure. The other case is sometimes we do, but the spacing is too large so that we may have a local buckling failure, which is a failure mechanism for the beams. All right, so this is the equation for laterally supported Y-flange beams. If the support distance, unsupported length or unbraced length is going to be either 0 or very small, less than L sub P. I'm going to talk about L sub P and L sub R later. Then we can fully utilize this capacity, which is MP, the plastic bending moment. And we can calculate MP as Fy times Z. And what was Z? Plastic section modulus. We already talked about that in the class, right? So Fy times Z is going to be the maximum moment capacity. And if we have either 0 unsupported length or less unsupported length less than L sub P, then MP is going to be the maximum moment capacity. I'm going to skip this slides because we already talked about that, right? Under the positive moment, we have a kind of a fight between the compression portion and the tension portion. So it came up to the final failure mechanism as a lateral torsional buckling based on their they compromise the failure mechanism. So this is the final thing. So we have a little bit of the translation in the downward, and then we have a rotational movement. So that is called the lateral torsional buckling. So this is the main failure mechanisms for the beams. And our M sub N is going to be less than MP. It could be equal to MP when the lateral torsional, when the unsupported length is going to be small. So let me go to this one first. So we already talked about this in the class, and it is very similar to the chart for the buckling failure for the column, right? So let me just change the color. So this is the portion where we can maximize the capacity of our beams. So Mn, our nominal moment, is going to be equal to MP, which is Z times Fy. And this is the reason that we have some reduction of our moment capacity due to the less support, lateral support. So here we have two guidelines, L sub P and L sub R. These are two values that we can determine whether we have M sub N is going to be in this range or the other range. And LR and LP and LR equations are available. Let's see, go back to a couple of slides. So this is the equation for L sub P. As you can see, L sub P is in terms of R sub Y, which is a radius of gyration about Y, the weak axis, and material properties E's and Fy. So here we have to prevent the lateral torsional buckling, which means we can maximize and utilize the full capacity of the beam, and we have to satisfy this equation, which means the maximum value of unsupported length or unbraced length L sub B within that range is going to be LB it will be equal to 1.76 times Ry times this, which is this. And we call that L sub B, the corresponding L sub B as L sub P, which is a limiting unbraced length for yielding. And that value is from this slide here. This is L sub P. So in other words, if your unbraced length or unsupported length L sub B is less than or equal to L sub P, then your MN, the nominal moment, is going to be equal to MP, which is Z times Fy. If your unsupported length or unbraced length L sub B is larger than L sub P, but less than L sub R, then you are in this range. So you have lateral torsional buckling failure, and the corresponding equation for figuring out your nominal moment is going to be this. So, okay, so I talked about L sub P now. So L sub B, that's a variable, is simply the unbraced length. L sub P is the maximum unbraced length that would allow the plastic moment strength, which is M sub P. If L sub P is exceeded, the member will buckle laterally before plastic moment is achieved. So what does mean? What it means is that if L sub B is larger than L sub P, then we have to consider the lateral torsional buckling. So we cannot maximize our capacity as M sub P. We have to instead use these equations to figuring out. L sub R, that's the boundary between elastic and inelastic lateral torsional buckling. So L sub P was for plastic lateral torsional buckling, or I would say inelastic lateral torsional buckling. It's very similar to inelastic buckling and elastic buckling for the column, right? And L sub R is for elastic lateral torsional buckling. So I would say this is the range for inelastic lateral torsional buckling range. If L sub B is larger than L sub R, here we are in the elastic lateral torsional buckling. And the equation for L sub R is really, really complicated. It looks like this. And I just want to introduce you because it is there and it is available in the steel manual, but we are not going to use this equation in any calculation. So let me just show you the L sub R and L sub P, L sub R values from the steel manual, how we can find out those values from the manual. Okay, so let me go back to this document camera. So I'm gonna open up the chapter 3, which is, chapter 3 for part 3 for the flexure members. And the first table is for C sub B value. So I'm gonna go on to the table 3-2. And this is the first page of table 3-2. And the organization and the structures is gonna be exactly the same for other pages as well. So the first column is a shape, okay? And the second column is for the plastic section modulus Z. And then we're gonna talk about these later on. So MP, MR, BF, best friend. We're gonna talk about that in a minute. And then you can see L sub P, L sub R values here. So basically, when you select a certain section, you can easily find out these LPLR value without having any calculation directly coming from this steel manual. So let's say you pick W40 by 655 section for your design or your project. L sub P value is going to be 13.6 in feet. L sub R value is 69.9 in feet, which means if you have your unbraced or unsupported length less than 13.6 feet, then you can fully utilize the maximum capacity, which is M sub P, Fy times Z as your moment capacity. If your unsupported length is larger than this, but less than 69.9 feet, which is really, really long, right? The large number here. Then your capacity is going to be reduced but so you're in the inelastic lateral torsional buckling range, and we have a corresponding equation to calculate that value. Okay, so I'm gonna stop my video, the first video here, and then we're gonna go over the next slide in the second video clip. All right, see you soon.